quantum technology. So keeping this in mind, of course, we have made quantum optics a major theme of this year's QIQT. So this is, of course, myself, Nirmallo Ghosh. So I am, of course, here at Department of Physical Sciences at IIST Kolkata. So I have been given the responsibility to moderate this session. So today also, as you have seen, that we have heard 3 talks, all on quantum optics. And now we have in this session, also we have 2 more talks, which are mostly in quantum optics. And we have 2 very distinguished speakers. And the first post these 2 talks of 1 hour duration, which is supposed to start at 3 o'clock. And first of all, speaker is Professor Solomon Ewan from IIST, Thiruvanathapuram. So to briefly introduce, of course, Professor Solomon Ewan is currently Associate Professor at Indian Institute of Space Science and Technology at Thiruvanathapuram. And his expertise, of course, is in quantum information theory. And his current research interests are in quantum optics and quantum information, and also in classical optics. And of course, as you can see that his talk, the title of his talk is Ameliorated Phase Sensitivity in a Mach-Zehnder Interferometer. So I guess this is related to basically enhancement of this phase detection sensitivity towards the quantum limit, which is, of course, a very interesting topic. We would like to thank Professor Solomon for accepting our invitation to deliver a lecture here. So without much more delay, I would give it to Professor Solomon. So over to you, Professor Solomon. Professor Solomon, can you hear?
Can you hear me now?
Yeah, you are audible. Perfect.
Yeah, so thank you, Nirmala, for this kind introduction. So, yeah, so today I'll be talking on this ameliorated phase sensitivity in a Mach-Zehnder interferometer. Okay, so let me go to the outline. So the way I have planned the talk is, first I will introduce to everybody what is the Mach-Zehnder interferometer, a very elementary introduction to that. Then we go into quantum treatment of the Mach-Zehnder interferometer, and after that I will discuss what we call as the quantum Kramer-Rao bound with regard to some phase sensitivity. Then I will go over to the discussion on how using intensity measurements, typically, how is basically we estimate phase through the intensity measurements, intensity which we measure. And then, here I will tell you the quantum version, how is phase sensitivity related to intensity measurements. Then I'll briefly discuss what we understand as a standard quantum limit. Then go on to a discussion on, whatever states with improved phase sensitivity over and above the standard quantum limit. Then I will outline some, this still here will be the discussion will be very general, all known stuff priori done. Then we will here now go to some a modified scheme of the Mach-Zehnder, where I'll outline some recent work one of our students here carried out, which will give us a enhanced sensitivity, phase sensitivity basically. So let me start. So this is the outline of the Mach-Zehnder interferometer. So you have a 50-50 beam splitter here, a 50-50 beam splitter here. Light can enter in 2 arms, then split through this beam splitter, then recombine, then travel across through each of the arms, get reflected in mirrors M1 and M2, and then in one arm you introduce a phase object, basically a transparency, a glass, or a transparent object. Any transparent object can act as a phase. Then the beams are recombined in this beam splitter, and then basically we measure the intensity at either of the arms or both of the arms. And the idea is these intensity measurements which you can carry out here in this arm and this arm is a function of this phase which has been introduced in one of the arms. And the idea is so you retrieve the phase from the measured intensities at both these arms. Okay. So this is the basic outlay of a Mach-Zehnder interferometer. In the quantum mechanical analog, what we have is, light is, represented by a state psi in together. In total, psi in is entering both the arms. Whatever then they recombine pass through the arms of the Mach-Zehnder, then recombine at beam splitter BS2, and then it produces psi out in totality at the two arms of the output. So this is the Mach-Zehnder interferometer picture that we have. Now let me come to the quantum mechanics. So before we go to the quantum mechanics of the Mach-Zehnder interferometer, so typically light, is a wave. So there are an amplitude enters in either of these arms, and it is the amplitude which free propagates through the arms before recombining, and intensity that we measure is the modulus of the amplitude which is a wave which is propagating in through the arms of the Mach-Zehnder interferometer. Now in this regard, when we say we want to quantize the do the quantum mechanics of a Mach-Zehnder interferometer, the understanding is that there are mode operators entering into these arms, and it is this mode operators which evolve as they traverse across the interferometer before recombining at the second beam splitter. So now let us introduce this bosonic operators A1, A2. So they satisfy this. So these represent the photon basically, and they satisfy this commutation relations. Okay. So using this, so there are two operators basically A1, A2, which enter these two arms. For example, this can be A1, amplitude A1 represented by mode operator A1, and amplitude A2 represented by mode operator A2 entering into each of the arms of BS1. Now, so with these operators at our disposal, we can construct these operators, these Hermitian operators Jx, Jy, Jz in this manner. For example, Jx is half times A1 dagger A2 plus A2 dagger A1. Similarly, Jy is minus I by 2 A1 dagger A2 minus A2 dagger A1, and Jz similarly is half of A1 dagger A1 minus A2 dagger A2. You see, this Jz is nothing but the number difference, and when we number difference at of the two modes, and number is essentially the intensity. Number of photons is essentially the intensity that we measure in the arm of an interferometer. Okay, so this is how we get the the amplitude is A. The intensity, for instance, is A dagger A. Okay, which is the photon count basically. Now, with this at the background, it is readily checked. We can check that Jx, Jy, Jz satisfy this commutation relation, which is the angular momentum commutation relation which we encounter in quantum mechanics. Now, with this, so as I said earlier, so the number operator, total number of photons, basically our total intensity that we measure is captured by this operator A1 dagger A1 plus A2 dagger A2. Now, with this defined as n, you can check that this J square operator turns out to be n by 2 plus into n by 2 plus 1. Okay, so you have this correspondence between. So given that we have represented it with modes, basically, so if you have two bosonic modes A1, A2, then we have a corresponding harmonic oscillator at the background, that we understand. So there are, you have Fock states corresponding to that harmonic oscillator modes. And now using those Fock states, which is N1, N2 for corresponding to operators A1, A2, we can, if you take this product state N1, N2 in the Fock basis, that turns out to be the MZ eigenstate in this representation. That means Jz is defined as this. If you take this product Fock state, we get essentially J comma M at the Z basis basically. Okay, so and vice versa. So you can retrieve, you can write J as N1 plus N2 by 2 and the M as N1 minus N2 by 2. Okay, so now let me go to the next thing. So now the interesting thing about this is, so any lossless optical element such as a beam splitter is represented through this unitary transformation matrix U, which is e power I theta n cap dot j cap, where J is this vectorial equivalent of this Jx, Jy, Jz. This is like Jxi plus Jy j cap plus Jz k cap. That will give you this vector J, and n cap is some oriented vector, unit vector. And what we find is that if you take this kind of a unitary, conjugate this mode operators A1, A2, we get a unitary, two-dimensional unitary transformation which acts on the mode operators A1 and A2. Okay, so this, if this capital U is exponential in J operator, and when you do the conjugation, you get the mode operators A1, A2 to transform as through this calligraphic U, which is a SU2 matrix. Okay, so now a simple example. So suppose we take unity transformation e power I alpha jx, you can verify that this transformation holds basically. So it will transform as some cos alpha by 2, I sin alpha by 2 minus I sin alpha by 2 and cos alpha by 2, acting on A1, A2 through this conjugation. Likewise, okay, so now for a special case of alpha equal to pi by 2, we get this matrix transformation, which we understand to be one version of a 50-50 beam splitter basically. Now you can see that these amplitudes are getting superposed with this transformation, which acts through conjugation, relates the mode operators A1, A2 through this 2 cross 2 matrix, which means that the resulting mode operators are an equi superposition of the input mode operators, for example A1 and A2. Okay, so it is in this sense that this conjugation captures the traditional classical beam splitter relation as acting on amplitudes A1, A2, except that now we have mode operators A1, A2 instead of classical field amplitudes A1 and A2. So likewise, you can check that using Jz, you get this kind of a relation. Yeah, so Jz conjugated on A1, A2 column vector will give you this kind of basically, this you can recognize it looks like the exponential of the Jz matrix in spin half. Okay, and similarly, this Jy conjugation will give you a two-dimensional rotation of A1 and A2. Okay. So now let me, with this at the background, one other relation which we also know is that these Jx, Jy, Jz on conjugation with this, these are operators. Now exponential alpha of Jx is a unitary, you conjugate with this unitary. These operators now transform like a three-dimensional vector. That means, okay, so which we understand quantum mechanics as Jx, Jy, Jz are vector, is a vector operator. So that is essentially what is contained in these three relations. Okay, so previously we have seen how the amplitudes transform. Here we see how the J's transform under conjugation by the same unitaries. Okay, so with this at the background now, let us go to the quantum mechanical Mach-Zehnder problem. Okay, assume that if you assume that psi in is entering these two arms, then this 50-50 beam splitter, you can use this relation for this 50-50 beam splitter, this relation in this relation. Then you pass the mode operator through, this arm, this mode experiences a phase, which means that particular A, that amplitude which is going across this fellow experiences a phase. So that is understood like from this transformation. You can see that, this transformation relation Jz, for instance, captures, that the phase A1 acquiring a phase of e power minus I phi by 2 and A2 acquiring a phase of e power minus I e power plus I phi by 2, which means A1 A2 relatively acquires a phase of e power I phi. So this exponential operator basically captures the fact that you are able to that you have introduced a phase object in one of the arms of the interferometer. So you perform all the necessary algebra. That means you can do either take the psi in and evaluate psi out, or you can take mode A1 and A2, do the evolution on modes A1, A2, and then find the final output annihilation operator mode operators, and then execute it on psi in. Whichever way you do, you get this relation in the end. That means psi out is related to psi in through this transformation. That is, psi out is equal to e power I pi by 2 jx, e power I minus I phi jz, e power I pi by 2 jx, and which can be further simplified as psi out is equal to e power I phi jy psi in. This is a very important relation in this context, which means what we have here is, if you send in psi in through two arms of this interferometer, and you have introduced a phase object here, and you have got a psi out emerging at the other two arms, output two arms. This psi out looks as if it is evolved through the phase phi through jy operator as acting on psi in. So this looks like a parameter evolution. Basically, psi in is some exponential of Hamiltonian times some phi, which is the parameter which gives you psi out. This is a conversion of whatever we understand in traditional interferometry as phase object being introduced in one of the arms of the interferometer, now is seen to be a evolution parameter relating the input state with the output state. So with this at the background, we have what is the quantum Cramer-Rao bound. So the idea is the following. So suppose you have a state evolution which psi out is related to psi in through this exponential relation. What is the minimum, the fluctuation that you can get on this evolution parameter phi in general? Okay, this and this lower bound on this, the fluctuation in phi, that means minimum fluctuation in phi as pertaining to this relation is given through this inequality, which means delta phi is greater than or equal to 1 by n, where n is the total photon number, means total photons entering the Mach-Zehnder interferometer. Okay. So a proof of this is available in this book by Hellstrom, quantum detection and estimation theory. So you can look at the proof there. This is basically, what is the minimum variance, you can get on this kind of an evolution relation. And in this case, you can, if you calculate or do out a detailed calculation with this in perspective, with the Fock basis as being, JM and so on, all that, we get this interesting relation. Okay. The idea is that whatever you do, whatever measurements you do at the output of the Mach-Zehnder interferometer, when you estimate, you are the fluctuation of your estimate can never go lesser than 1 by n, where n is the total number of photons entering the interferometer. Okay. So now, so this is very general. This quantum Kramer bound doesn't tell what kind of measurements you need to do, how you do the measurements. It is a inequality with the most general picture in mind. However, in lab, what we actually measure are observables. Okay, so for instance, in this interferometer, one way of typically estimating phase is through what we understand as the intensity difference measurement, which means you measure intensity in this arm, you measure intensity in this arm, take the difference. That difference is a function of this phi, and then you try to invert that relation to obtain an estimate on phi. So what the quantum Kramer bound gives is that whatever you do in your in your estimation process, the fluctuation phi in your estimation can never go lower than 1 by n, which is the total number of photons entering your interferometer in the first place. So, but in lab we actually measure intensity. So here, for example, so if you assume that in observable, there's an observable, which is for instance the intensity which you measure at the output. So if you calculate the fluctuation of this operator, intensity is nothing but A dagger A, for instance, or A dagger A output dagger A minus B output dagger B, for instance, which is the difference of the number operator at the output. That can be thought of as O. If you, and the fluctuation of that O is related, quantum mechanically through this relation. Okay. So since we are measuring intensities, for example, like as denoted here, like A1 dagger minus A2 dagger A2 at the output side, then so basically we can take the expectation value of this difference number operator at psi out, calculate its square, and then also take expectation with psi out, and we get an expression for the fluctuation of this number difference operator. And so we have this simple error propagation formula, as it is said. The fluctuation O is a measure of the fluctuation in phi, which you can invert. Basically, delta O of out is nothing but delta phi into this modulus of dou O of expectation of O out by dou phi. So you get this delta phi is nothing but delta O out by this expression. Okay. So this is estimate. This expression is giving you a fluctuation phi as obtained from using, say for instance, this number difference operator for your measurement. That means you want to invert for phi using this number difference operator. Then the fluctuation phi is as good as your fluctuation in the O operator as evaluated on the quantum mechanical state that emerges from at the output ports of the Mach-Zehnder interferometer. Okay, so now, so if you do the algebra, so here we can perform, you do this D out, so you get, you can rewrite this number difference in terms of the Jx, Jy, Jz operators, and some piece of straightforward algebra, you get this kind of a expression for D square out, D out. Then you can calculate the variance in phi as estimated. This is the variance in phi which you can expect by measuring this number difference operator through this expression. Okay. Now, if you have, so what we understand is if you put actually in this input of this Mach-Zehnder interferometer, if your psi in is a coherent state times vacuum. Basically, coherent state is nothing but a typical laser beam coming out. For example, standard 639 nanometer laser is a Gaussian beam which exists a laser, and that beam in the quantum mechanical sense is understood to be the coherent state, for example. So, with amplitude, you can write down amplitude for that laser beam entering in this arm, and suppose you inject no light here, that corresponds to alpha tensor 0 as the input. Means you are illuminating this arm with a laser, here you do nothing, and then you try to do the interferometry to measure the intensity difference. So now if you did that kind of input, that means you inject a coherent state in one arm with ground state on the other arm, and you can calculate using this previous expression, using this intensity difference, phase uncertainty as expected from intensity difference measurement. If you calculate that at phi equal to pi by 2, we get this expression, that is delta phi is 1 by root n. Now you can actually parallelly check through this actually for this kind of input using this inequality, this quantum Cramer-Robb bound for this input state. That will also give this delta phi is greater than or equal to 1 by root n, which means in this case, by doing intensity difference measurements in and around, suppose you introduce a phase object of the size of pi by 2 and the phase, the path difference or thickness is for that given lambda is around pi by 2. Any small deviation from pi by 2, the sensitivity of phi in and around pi by 2 is of the order of 1 by root n, and QCRB, which is an independent of, which is a more general statement, it doesn't pertain to intensity difference measurement. Say that expression also, that QCRB also gives us lower bound as 1 by root n, which means we have achieved the quantum Cramer-Robb bound of 1 by root n by doing intensity difference measurements at the output of the Mach-Zehnder interferometer for this input state, which is alpha tensor 0 at and around phi equal to pi by 2. That means we are able to saturate the quantum Cramer-Robb bound at phi equal to pi by 2 for this input state. Okay, so that is the content of this slide. So now, so the question was, so this is like going as square root of n, which is the, n is the number of photons entering the Mach-Zehnder interferometer, which is the mod of alpha, which is the of alpha being the displacement of the coherent state. So now the question was, can we do better than this? So instead of taking a typical laser beam and then doing the interferometer with interferometry with that kind of a beam, can we go lower than 1 by root n? So the first paper which so now we'll discuss some known results and some new results as well as known results on states, input states with which will give you improved phase sensitivity. So first work this regard was of that of Carlton Caves, which is the quantum mechanical noise in an interferometer. I'm not going to go into this paper simply for the reason that this paper, as I understand, deals with what we understand as a Michelson's interferometer, not the Mach-Zehnder. The analysis is very similar, and for that situation, in the Michelson's interferometer case, this paper showed that using a product of a coherent state and a squeezed vacuum as input, you can go better than this 1 by root n limit in for this fluctuation phi, which we can obtain by measuring the intensities. So this paper gives that if you actually use what we call as non-classical or truly quantum sources of light, we are able to improve upon this delta phi equal to 1 by root n. That means this denominator can be larger than root n. And quantum Cramer-Robb bound simply says that you can at most go as 1 by n. Okay, so typically the goal has been how to improve, how to, so if you use classical light, you get 1 by root n. Then using quantum light, can we approach the 1 by n limit for the fluctuation phi? So with the first paper which gives that such a thing was this important paper by Carlton Caves. This is a very famous paper, and as I understand, this is the basis of what we understand today as a LIGO interferometry experiment. Okay, that is built on this work basically. So now coming back to the Mach-Zehnder interferometer. So in 1986, whatever I've outlined, the theoretical outlay of the quantum mechanical Mach-Zehnder interferometer is detailed out in this paper by York, McCall, and Clodder in 1986 Physical Review A. There they considered this kind of a state. So I'm, instead of using the Fock basis, I'm using the angular momentum basis to represent the state. So it's we denote here is as the YMK state. So you take psi input of this form. For this, you can calculate out the phase sensitivity delta phi. It turns out to be 2 by root of n into n plus 2. Similarly, in 1998, Dowling wrote a Physical Review A paper where this kind of state was considered. So here you can note that this J is integer J. The n1 photon numbers n1 n2 are chosen such that we get integral J. Here it is half integer J. And for this state, Dowling showed that you can get a delta phi of 2 by n plus 1 in and around phi equal to 0. Here also likewise for the York, McCall, Clodder state, at phi equal to 0, we get delta phi to be this. So see here we have again, we are not yet reaching, it is not still 1 by n. It is like 2 by n or 2 by n plus 1 of that order. The question was, can we improve upon this from this 2 by n plus 1 kind of sensitivity or fluctuation phi and approach towards 1 by n. So now we consider examples, what we could, whether we could do better. So you take this, fictitious psi in, this so we have introduced some parameters into this state. So you have root of p by 2 j of 0 z, root of p by 2 plus j of 1 at z, plus these two other two terms. So after a lengthy piece of algebra, you will actually calculate this expression for delta phi at phi equal to 0. Similarly, you take this kind of input, which is p by p times j 0 of z, and then with these factors of j1, j minus 1, and j2, and perform the necessary algebra, you at phi equal to 0, you find the delta phi to be this expression. Okay, and now p is like a probability basically which can vary from 0 to 1. So that is a generalization of these kind of states basically. So here there are only 2 and with 1 by root 2 coefficient. So now we liberate that constraint and put a parameter, and we superpose the nearby states also. Instead of 0 and 1, we go j minus 1 and j2. Here also we go both sides, j minus 1 and j2. Here, so here this example 1a and 1b is for integral integer j. Now so when you do the analysis, so basically, so we are summarizing some result here. So you, on the left side of the plot, you take average n times delta phi. Here in the y-axis, the x-axis, you plot the log of average number to the base 10. So basically, you can understand that larger the smaller this n into delta phi, better your sensitivity. Okay, so here we plot, so what we plot as 1 corresponds to the YMK state. Then 2 corresponds to the example 1a considered here for P equal to 0.95. And then similarly, for example, 1B, which is this example, you put P equal to 1B and calculate out delta phi, and then do n delta phi. You make this plot, and then this is what we find. And 4 is nothing but the ultimate quantum Kramer-Rao bound, basically 1 by. So basically, if this is n into 1 by n is 1, so this is the 1 for all n. So clearly we can see that, you know, for the states 2 and 3, which are the examples which we have considered, they are better than the YMK state, but they are not yet close to the ultimate limit. Okay, so this example we consider for j equal to integer j, basically. So these compare with the YMK state. Now going to, you know, do a comparison with the Dowling state. Now we take this kind of superposition. So Dowling had only j 0.5, j minus 0.5. Now to the side you add j of 1.5 and j of minus 1.5 with these factors. So the p is a variable and p is like 0 to 1. So you calculate as before the delta phi and you end up with this kind of an expression at phi equal to 0. Similarly, another example of, you know, what we call as example 2b, you do a perturbation of the original Dowling state with the side thing, and in the parametric, in this kind of parametric form, you get delta phi, this kind of expression for delta phi at phi equal to 0. And same analysis we repeat. So here, you know, 1 is the n delta phi for Dowling state, 2 is for example 2a with p equal to 0.95, 3 is for example 2b with p equal to 0.95. For increasing n, basically log n basically means increasing n photon number. So here we have gone up to, as you can notice, you know, up to 10 power 9, just to, you know, make it comparable to lab scenario. You know, if you eliminate in a lab experiment, you will get of this order of number of photons, basically. And here, as before, 4 plots the ultimate quantum Kramer-Rao bound, basically. So n into 1 by n is 1. So this is the ultimate which we can reach. Okay, so now there is a question. So these are all nice superpositions. Okay, so you have constructed some superposition. Okay, this is some engineering you have done, and we have done some state engineering, you know, by perturbing it this way, that way. And so the question is, they are very, you know, they look very artificial in nature. Meaning, is it really possible to create them experimentally? Meaning, do we have ways to generate? Can you excuse me just a minute? Yeah. So to continue the discussion, so these states look very, you know, artificial sense, like you know, they are very particular superpositions of this JM basis states. So the question is, can we actually experimentally? Is there a way to realize them experimentally, or anything, at least from known experimental schemes which is available in literature? Can we actually generate this kind of a superposition? This kind, or even for you know, j equal to integer cases of this kind, basically. So to answer that question, we consider what we call as the modified scheme. So this is the modified scheme of the thing. So what is the idea? So, you know, so this modified scheme, let me say, is not like, you know, it's not a very straightforward. It looks simple in configuration, but you know, literature, as per literature, you know, people have tried several things, several kind of modifications to achieve an improvement over the known states like the YMK or the Dowling states. So here, after a lot of trial and error, we came up with this kind of configuration. So what is the idea? You inject basically, before anything, you inject the Fock states 1 tensor 0. So you inject a Fock state 1 here, here you inject nothing, which is the ground state. Then you squeeze them through single mode squeezers, S of Xi1 and S of Xi2. So experimentally, as we understand from literature, this is perhaps possible experimentally. Okay, so then, so the idea is you have a concatenated Mach-Zehnder interferometer setup. So what we do is you inject this 1 tensor 0 here, you squeeze it, single mode squeeze it. These phase shifters like -π/2 +π/2 are phase shifters. Then we pass it through this beam splitter to recombine. So it is this beam splitter which combines this squeezed 1 tensor 0, single mode squeezed 1 tensor 0, and this whatever output we get from this combination through this beam splitter acts as the input for our standard Mach-Zehnder interferometer. So this part of the modified scheme is nothing but the goal here is to generate a desirable input state sign, which will perhaps achieve better than, say, for example, 2 by n plus 1 and approach the 1 by n plus 1 limit. Okay, so the role of this extra arms or extra Mach-Zehnder kind of thing here is nothing other than to generate this, a desirable sign in this at this 2 inputs of the standard Mach-Zehnder interferometer. And as before, this this block is a standard Mach-Zehnder. Whatever we are doing here is nothing more than to generate the desired 2-mode input, which will enter the standard Mach-Zehnder. Okay, so this is the modified scheme. Now, so you can do all the algebra as outlined in the the first few slides. You can actually now calculate out starting with this sign here as 1 tensor 0, putting 2 single mode squeezers and recombining with BS1 mirrors M1 M2, reflect it, then recombine at BS2, then again reflect, then pass through this phase object which is of interest, then again recombine at BS3, which is to get the psi out. If you do all the algebra in getting the relationship between psi out and psi in, we get this transformation relation. Okay, and as before, this phi is the parameter of interest which we want to estimate. So here S of Xi is this single mode squeeze operator, and these are the standard relations which is available in any standard textbook, corresponding to how the mode operators transform under a single mode squeeze operator transformation. So now you do all the, again as before, what do we do? We take intensity difference measurement at this output. Okay, so and then from that we want to estimate phi to the best possibility. So if you do the necessary algebra, so you get the intensity difference measurement at the output gives this kind of an expression. Then d square out is this kind of an expression, and ultimately at phi equal to 0, delta phi is this relation, and here u is nothing but this tensor product of this 2 single mode squeeze transformations. Okay, so this is the expression we get for delta phi at phi equal to 0 in the modified scheme with 2 single mode squeezes at the input. So now with this at the background, so we consider 2 schemes basically. So we can now at our hand we have at our disposal that we can vary this squeeze parameters Xi1 and Xi2. So in the first what we do is choose Xi1 to be R and Xi2 to be minus R. That is the squeeze in the 2 single mode squeeze operators. We choose the squeezing parameters to be R and minus R. So actually, so if you perform all this this piece of calculation, outlined here in this slide, we recover delta phi to be 2 by n plus 1 at phi equal to 0, interestingly. Okay. See, which is nothing but a Dowling limit. Okay, so this is precisely the expression Dowling obtained using finite dimensional states, meaning superposition of product Fock states, and J is finite. Now here we have a genuine continuous variable input, basically no restriction on the J, and surprisingly, if you do all the algebra, it reproduces precisely this the Dowling state limit, which means what we have for this kind of squeezing choice in this modified setup, if you inject, you S of this is R and this is minus R, you inject 1 tensor 0, then if you take the intensity difference at the output and ask for phase sensitivity at phi equal to 0, it reproduces for you 2 by n plus 1. Okay. So now obviously if this can reproduce 2 by n plus 1, then can a variation in the squeeze parameters produce better? So that was the question. So what we do is, so we define what we call as unbalanced scheme, where we set R1 not equal to minus of R2 basically. So you again some lengthy piece of algebra, you go over all the algebra and you get this expression for delta phi at phi equal to 0. Now this expression we have R1, R2 at our disposal to see if which will give the lowest phi as per this expression. So we do that numerically, and then so the numerical analysis is performed, and what we find is so as before, this is nothing but the standard ultimate quantum limit, which is 1 by n. Basically, n into 1 by n is 1, which is a constant in this graph. This 1 corresponds to the balance scheme, which will reproduce the Dowling expression for you. Now 2 is by optimizing over these squeeze parameters R1 and R2 by choosing them differently, and then running a numerical check of seeing which is the best possible. We obtain this 2, which is lower than 1, means you are able to get better than the Dowling limit, but not close to the ultimate. Still there is a gap between ultimate limit and what this state achieves. Okay, so this is another one result. Then so here we have considered no noise. Basically this is something like an ideal interferometer setup, and as if there is no noise entering in any arm. So the question was, does noise affect your sensitivity? So to that end, so we consider the modified scheme with noise. So basically the noise is injected through these 2 beam splitters, which is introduced in the standard Mach-Zehnder. So you have this phase object phi, and for theoretical consideration, we have assumed that noise is introduced just after the phase has been acquired, and in this arm it is anyway injected with or without meaning directly. Here we assume that after the phase has been acquired, we inject the noise. So noise is nothing but basically a beam splitter. Input of one of the arms is a thermal state basically, which is measured. This N0 is a measure of the noise entering here, and that is mixed with the incoming light to produce a noisy signal basically. Likewise here, and kappa is the root of kappa will give you transmittivity of these beam splitters. So this sort of gives a model for noise being injected into the standard Mach-Zehnder interferometer. So can the obtained states perform better than the known states even under noise? So that question is there. So we ran over all the analysis. We put some noise into the system to check whether we get sensitivity for better sensitivity for varying the beam splitter transmittivity as well as varying noise of the noise that is injected in the other arm. Okay, so we find that for small regions, for small, transmittivity closer to 1 with some finite noise, the considered states actually can do slightly better than the Dowling state or the YMK state, even in the presence of some noise. So that is a summary of these two plots. So I don't want to go into the actual details. So basically the takeaway from this these two plots is that even under noise, you can have a situation where this kind of a state, that means this this kind of a state chosen with unbalanced scheme, can produce in the presence of noise better sensitivity than, for example, this 2 by n+1 limit. So anyhow, in this slide I've explained this plots, but okay, so let me not go into it because it's very detailed. So that's it from my side. So this work is published in a recent work, which is this in quantum information processing. So Jayant was our MTech student at IIST. Now he is a scientist at PRL with Professor R.P. Singh. So he's setting up some quantum experiments there. So is Jayant around here now? Hello?
Yes, sir. I'm here.
Yeah, okay. So if anybody wants to ask any questions, you can shoot it to Jayant because he is the expert in this paper. Okay, so he knows this phase estimation problem thoroughly.
Yeah, that's okay. I can say. So the first question is: are there any cases where a weaker phase sensitivity is required? So yes, like in ultra precision measurement, suppose like as Solomon sir mentioned, like in the LIGO gravitational setup, what they actually use is a squeezed light interferometer, where you are actually able to measure deviations in phase up to a very small amount. You need extremely precise phase measurement. So in such ultra precise measurement schemes, you would actually benefit from a weaker phase sensitivity. Also, like even like one application is where we use interferometers to measure any like imperfections in our mirrors or anything. So in that way also, if we have a better phase sensitivity, it will be advantageous so that you can measure accurately. Hope that answers that question. The second question, yeah. So the change from Fock basis to angular momentum basis, so it is just for like ease of calculation. So there is since like all the optical instruments in that Mach-Zehnder setup, it can actually be represented using angular momentum operators. The calculation would be easier if we change it to an angular momentum state basis. You can do the calculation in the Fock basis also, but it would be more tedious. So that's why the change in basis is preferred. Okay. Specialty about phi is equal to 0. Yeah. So most of the setup, the interferometric schemes that is presented here, they actually have let us say an optimum range where they have maximum sensitivity. So what we found in our analysis was that at phi is equal to 0, it gave the maximum sensitivity. So what I think it should be done.
Jayant, maybe let me interfere. No, the thing is, see, if you assume that whatever residual, if you're able to balance the two arms, what we want to find is the in and around. Suppose we are able to get an alignment and put the correct phase shifters in each arm of the Mach-Zehnder, so as to get null fringe, for example. Null fringe basically means delta phi is 0 basically. If you are able to align, and then we want to sense some phase object which is very slightly away from the null fringe. So that is why experimentally, you assume that you got a null fringe condition, and then you want to see perturbations on the null fringe. Then, delta phi in and around phi equal to 0 becomes relevant.
Yes, sir. Yeah. that.
Okay.
Yeah, that is.
Okay, thank you, Dr. Salman, for a very nice talk. If there is any further questions, of course, we can take. Otherwise, we will, of course, thank Dr. Salman once again for a nice presentation on enhancing phase estimation sensitivity in Mach-Zehnder interferometer. Any other questions? One can put in the chat box.